Godot Tutorials is not sponsored by or affiliated with the Godot game engine. Before I begin, I just want you to know that this episode's coding example will be uploaded to GitHub in the description link down below. So if you don't want to sit through this episode, feel free to check out the link to see coding changes from the last episode. It will be under the folder Pong-08. Let's get straight into it. The simplest form of dynamic collision that we can allow in our game for our player paddle is translating the contact point of the ball and paddle into a range between positive and negative values. For our speed vector on the y-axis, where 0 is the middle of the paddle. In this case, you need some basic math, and it is okay if you are unable to get the math down. Most people find the mathematical formulas from Google in most cases, but the most important thing is trying to understand what the math is doing. And with learning anything new, it's okay that you don't understand what it's doing in the beginning, because at some point it will just click. In this case, let's take a look at the Warmup Map. In this case, we have 4 different points on our player paddle that we use to detect the ball collision with the player paddle. But when it comes time to reacting, all we really need are the y values along a single axis. In this case, we have our range, which includes y1 to y2, and those values can be anything as long as y1 is less than y2. And we do have a y3 value, which is the center of our paddle, which equals 0. And we have a ball, which also has an xy value, but for the ball, we only care about the y value. And that's because when the ball moves and makes contact with our paddle wherever it lands, based on where our paddle makes contact with the ball, we need to determine what direction it moves. For example, if we make direct contact with the center of our paddle, we would like to move straight. And in this case, if our contact point is closer to y1, we would like to move at a high angle at an upwards direction. And if our contact point is closer to y2, we would like our angle and direction downwards at a high angle. And anything in between center and y2, the angle goes downwards, but ever so slightly as we get closer to the center. And same thing for our contact point with y1. The farther away from the center we are and closer to y1 we get, the higher our angle is. And from this contact point, wherever it lands between y1 and y2, we would like to convert that into a new range, where again the center of our range is 0. And this is for our y value in our vector speed. And so to clean it up a little bit, this is what we have. We have a range from y1 to y2, and we would like to convert that range into the values of y4 and y5. On top of that, our y3, wherever it lands in this range, also needs to be converted into our new range, which will be y6. Now in this case, we are solving for y6, and so let's plug in some values. Let's do this by hand. So in this case, we have a value y1 equals 100, y2 which equals to 200. So in this case, our paddle is 100 pixels long, and it is 100 pixels away from the top of the screen and ends 200 pixels away from the top of the screen. And of course, our ball made contact on the paddle at the center, which has a value of 150. Now we would like to convert this range into our new range where y4 is negative 400, which means that our ball is going up. y5 equals 400, which means that our ball is going down. And notice here that the length of our new range is 800, but we don't know what y6 is. And so let's go ahead and create that formula. So first we must get y1 and y4 to 0. And you can think of this as sliding our range to 0 while keeping the length the same. And so in this case for y1 or range 1, what we do is subtract everything by y1's value. So in this case, y1 equals 100 minus positive 100, y3 equals 150 minus positive 100, and y2 equals 200 minus positive 100. And what this does is we slide our new range so that y starts at 0. Now, once we've gotten our new range to start at the value of 0 while keeping the length the same, so length 1 is still 100, now we need to get y4 to 0 while keeping the length 800. And so we do the same thing in this case, except we don't know what y6 is yet. And so what we have is y4 equals negative 400 minus negative 400, which turns this to 0, and y5 equals 400 minus negative 400, which turns into 800. And so that's what we get here. So now that we have y1 equals 0 and y4 equals 0 while keeping the lengths the same, now we can start trying to figure out what y6 equals. And to do that, all we have to do is expand our old range until it equals our new range. And so think of multiplication as growing or shrinking our numbers. So in this case, all we have to do is divide y5 by y2. In this case, 800 divided by 100 gives us 8. And then we take that 8 value and multiply it to every value in our old range. So 0 times 8 is 0. 50 times 8 will be 400. And 100 times 8 equals 800. So in this case, by multiplying, we are stretching our old paddle range to give us our new value for the speed on the y-axis. And so you can see here y3 is 400, y2 is 800, and it looks exactly the same as our new range. However, we are not done yet. Yes, y6 equals y3 in this case, because we've converted our old range into the new range. However, we need to get back to the original range that we had at the beginning, which was negative 400 through positive 400. And that's actually quite simple. All we have to do is subtract our old range by the original value of y4, which was negative 400. In this case, 0 plus negative 400, 400 plus negative 400, 800 plus negative 400 will give us the new range we wanted. And so in this case, when we do everything, we get y3 equals 0, therefore y6 equals 0. And so when y3 was 150 between the ranges of 100 and 200, that converts into 0 on the range of negative 400 and positive 400. Now, when we plug in the 0 for our vector speed on the y-axis, what we get is a ball moving in a straight line, either left or right, depending on x's direction, positive or negative. And so if we plug everything we did earlier into a formula, what we get is y6 equals y3 minus y1 multiplied by length 2 divided by length 1 plus y4. And of course, if we get length 2 and length 1, what that turns into is y5 minus y4 and y2 minus y1. And that is our simple range conversion formula. So in this formula, you can see that we need 5 values. And so in this case, we do have 5 values. First, we have the paddle points. Then we have the contact or ball made with the paddle. And all we really need to do in code is have the values of our speed on the y-axis. Now in this case, what we have is a range conversion for controlling magnitude and direction. And this is the simplest solution to add dynamic collision reaction to our player paddle and the ball, and the AI paddle and the ball as well. Now keep in mind that having a range that dictates the speed on the y-axis, we are both controlling the magnitude and direction of our ball. And so let's go ahead and take a look at an example. Here we have our ball speed vector, and of course, when our ball makes contact with the paddle, we would like to flip the speed on the x-axis, and we would like to have our new range on the y. And so in this case, if our ball hits the top portion of our player paddle, based on our formula that we just created, our range conversion formula, in this case, let's pretend our speed is 400. Now, in this case, our movement on the y-axis is small because our numbers are small, so negative 320. Now let's go ahead and change our range. And you'll notice that when our range changes, in this case, we doubled the range, even when our ball hits the same part of our player paddle, our velocity in the y-axis doubles. And so instead of negative 320, what we have is negative 640. And so just on the y-axis alone, we've doubled the speed along the y-axis. And so in this case, if our speed never changes value, but our y value grows and shrinks, then we are both changing the magnitude on the y-axis along with the direction of our speed vector, which is just basically a velocity. Regardless, let's say our ball hits the bottom of our player paddle. Notice that now our ball is moving downwards. And so this is the beauty of having a range conversion of our player paddle to some value on the y-axis for our ball speed. And if we hit the center of our player paddle, notice that there is no speed on the y-axis because the value is 0. Regardless, range conversion is the simplest and most effective solution to our dynamic reaction for our player paddle and the ball. If you wanted dynamic collision reaction between ball and player paddle, converting the numbers or using a built-in game engine specific function to convert ranges is the easiest method. You have the ability of converting different paddle sizes to different speeds on the y-axis. That means that no matter how big or small your paddles are, the range it converts to will never change. And in this case, player skill is now involved when playing our game. Despite our range conversion or min-max conversion being the simplest and most effective method, does come with negatives as is. The first negative would be that editing both our min and max values will increase or decrease both the rotation and magnitude. And that's because we tied our new range to the y-axis value for our ball speed value on the y-axis. And so increasing that or decreasing that will change both the rotation and magnitude that our ball takes. The second problem is that it's hard to visualize results, again, because if you're 0 on the y-axis but positive on the x-axis, you're moving in a straight line to the right. And if the x-axis is negative and y is still 0, you're moving to the left. However, if you're moving 400 pixels to the right and 400 pixels up, then you are essentially going 45 degrees. But what happens if 400 going up now becomes 800 going up? And so technically you'd be in between 90 degrees and 45, whatever value that may be, which is probably around 66 degrees. And so you can see that it's hard to visualize what our direction and magnitude looks like when we're just dealing with our ball speed vector value. And the last negative is that you have no real control over the direction or magnitude separately from the ball speed. And so you are reliant on controlling the ball speed vector values to determine direction and magnitude, and changing our speed vector, which is just velocity, has the potential to change both the direction and magnitude. To give us independent control over the rotation and magnitude separately for the ball speed vector, we need to use vector map. And so in this case, it's a slightly more complex process for changing direction and magnitude. However, the benefit is that we can control them separately, independent of each other. On top of that, this gives us the most control over reaction of the paddle and the ball. In my personal opinion, this is unnecessary complexity considering we are making a simple Pong game that will not utilize this feature of changing angles and changing magnitude. But regardless, in the sense that we want to add these features later in the future outside of this series, this is perfect for giving greater control of both rotation and magnitude for future power-ups and penalties to our ball speed and direction. In this case, the only two vector math we really need to understand is vector scaling and vector rotation. Vector scaling changes our magnitude only and does not change direction, and vector rotation changes direction without changing our magnitude. In a sense, the math is quite simple. You may need just a little bit of knowledge when it comes to trigonometry. However, you can get away from copy and pasting whatever you find through online searching. The real complexity comes from translating the math into code to fit the needs of our game. So let's just go over the math. Now, in my mind, I'm thinking the following to keep things simple for the series. First, start the vector at a straight line with a base velocity, in this case 400 on the x-axis, 0 on the y. The next step will be to convert the range of our ball paddle contact to a rotation value between positive 90 and negative 90, and apply that to our baseline velocity, which is 400 on the x, 0 on the y. Once we have this new vector value, we will then convert the range of the ball paddle contact again to a scale range, in this case positive 3 and negative 3. However, we will be needing to use the absolute value to turn that into a positive to make sure that our final value is on the positive x-axis. Lastly, to determine whether we go left or right will depend on what the last, or in this case, the current x value was. In this case, was it going to the right or going to the left, and apply that negative value onto the x-axis of our value. And that will be the final direction and magnitude for our new ball vector speed. In this case, let's go over the vector scaling first. It's actually quite easy. Again, vector scaling increases or decreases magnitude without affecting rotation. And all we really need to do is take our original vector value, multiply our scale value on the x and y axis values, return that back into a new vector value, and then return the new vector value. And that's pretty much it for scaling our vector. By doing this, we are able to increase magnitude or decrease magnitude without changing direction, because we are applying the scale value equally among the x and y axis values. So remember, multiplication is growing or shrinking. Anything over 1 will grow, anything under 1 and more than 0 will shrink. And of course, if scale equals 1, nothing changes. Let's go ahead and take a quick look at vector scaling. So in this case, y3 equals negative 110. When we apply the conversion formula, what we get is y6 equals 2.3. And so our scaling value, in this case, the maximum amount we will want to scale our vector speed will be between 0 and 3. However, for our conversion formula, we need to have negative 3 and positive 3. However, let's say our paddle hits up here, negative 190, the complete opposite of negative 110. Well, our y6 equals negative 2.3. However, when we make that value absolute, what we end up getting is positive 2.3. And so whether we hit on top or whether we hit on bottom, notice that the closer we get to the edge of the paddle, the closer we want to apply the value 3 to whatever our ball speed value will be after rotation. And so in a sense, if the player hits closer to 0, we don't want to apply a scaling value. However, the closer we are to the top or bottom, we want to reward the player and increase the speed to something faster. And of course, if we hit the center, even though this value will be 0, we need to make sure that in our code, the 0 value needs to be 1. And so anything less than 1 in our scale value needs to be 1. Again, the reason we need a value of 1 is because if we multiply anything less than 1 and more than 0, anything between 1 and 0, we actually make our scaling smaller. And that's not what I am looking for right now. And if our value is 0, then our ball just stays still because it's not moving in any direction or with any magnitude. And of course, we can use some if statements to make sure that our value is at least 1. Now, the beauty of what we have is that we can change our magnitude. So notice how it's 3 and 3. Well, if we wanted to, we could change this into 10, for example. So any value between 0 and 10 to scale on our ball vector. And depending on what your base speed is, maybe this is something you want and maybe it's something you do not want. Now, let's take a look at vector rotation, which is slightly harder to implement mathematically, but just slightly. Now first, vector rotation affects the direction without changing the magnitude. Now keep in mind that our formula needs to be done in radians, or an extra step of converting degrees to radians is needed. Now in this case, we can do the same thing. Notice how down here, y3 equals negative 110. And over here, you can see that we are going to use 89 degrees and 0. So basically anything between 89 degrees and 0 will be applied to our ball speed value. In this case, y6 equals negative 71.2, which is great because we would like our ball to go downwards. And so as you can see here, the closer we are to the bottom, the more angle our ball will have. And it's better if we just add the degree symbol, just to show that we are dealing with degrees and not just numbers, or these numbers represent degrees. And of course, if we hit towards the top, where y3 equals negative 190, this is positive 71.2 degrees, which is upwards. And as you can see here, the closer we get to the top of the paddle, the closer we are to wanting our ball to change to 89 degrees positive. And if we hit the exact center of our paddle, we would like to apply 0 degrees onto our ball, which means that our ball moves in a straight line, because we are applying rotation to the base speed, which again is 400 on the x-axis and 0 on the y. And the best part of this conversion formula is that we can change the values of our rotation. So instead of 89 degrees, we can change it to anywhere between 10 degrees and negative 10 degrees. And so just by separating our magnitude and rotation, we can visualize better what our paddle will do. So in this case, where 89 degrees is basically a full 180 on the right side, by having 10 degrees, we have a cone of a total of 20 degrees total. And so you can see that the more we increase the degrees, the more our paddle is able to move or change rotation. And so this is what I'm talking about when it's easier to visualize. The lower our degrees are, the lower our ranges for our degrees, the smaller our ball is able to move. And so instead of 89 degrees, which is almost 90, moving like this, what we get is a ball that can either go straight or it can just go ever so slightly. And so you can see the value of separating magnitude and rotation using vector map. Now let's go ahead and see what we need to do for vector rotation, and it's actually quite simple. What we have is an original vector with an x and y value, and based on the amount of degrees, or in this case theta, which we need to convert to radians, we can actually change the rotation of our vector without changing the magnitude. And the formula is on the screen. So our new rotated value on the x-axis will equal to x original multiplied by cosine theta minus y original multiplied by sine theta, and our new y value will be x original multiplied by sine theta plus y original multiplied by cosine theta. And that is how we are able to change, or in this case, rotate our original vector value to a new rotated vector value, keeping its magnitude. And over here, I have a pseudocode of our vector rotation. And even though it's slightly more complicated, it's actually quite easy now that we're just converting our math formula into code. In this case, we take in an original vector value. We take in the degrees we wish to change, whether it's positive or negative. We create a new variable that holds our vector2 value. We make sure to convert the degrees to radians and pass that into, in this case, a variable for radians. Then we have a sine variable, which we need to use a built-in function to take in our radians and convert that into a sine value. So in this case, this would be our sine theta. We do the same thing with cosine, in this case, cosine theta. And right here is where we rotate our original vector. And in this case, it's the same thing we had in our previous slide. Take the original x multiplied by cosine minus original on the y multiplied by sine, and original x multiplied by sine plus original y multiplied by cosine for our rotated y value. And then we return back the rotated value. And that's basically it. So let's go ahead and actually code this out and then figure out how we can apply that to our paddle class. Okay, let's go ahead and actually start creating what we need. And the lowest hanging fruit is to create a new class to hold our vector and point conversions. So first we'll head over to miscellaneous. We'll go ahead, right click. We're going to go ahead and pick new script. And in this case, it's actually going to be a resource script. From there, we can give it a name. And in this case, I do want to give it the name math. We can press create, double click on math, and voila. We extend from resource. Now let's go ahead and actually give it a name. And in this case, I want to give it the name math, to describe what this class will be doing, which is to hold all our math functions, which include our vector rotation. I'm going to go ahead and widen this, and then let's go ahead and create our point conversion, which, if you remember, we need 5 things. The point we wish to convert, the original range, value 1, value 2, and the new range, which is value 3, value 4, and that's 5 items, our function needs to hold. In this case, we need to get the length of our original range and the new range. So let's go ahead and create those variables now. From there, this is quite straightforward. All we really need to do is return our items. In this case, what we want to do is our original, or in this case, the point we wish to convert minus the original start. And then we want to multiply that by the new length and divide that by the original length. And then from there, we wish to actually add the new start value. So in this case, point A minus original start multiplied by the ratio between our new length and the original length, because that's what this is, a ratio. Multiply the ratio onto our converted point A and then add the new start value. And that's pretty much it for our static function for point conversion. Now, next, let's go ahead and start with the vector scaling. In this case, we do need a variable to hold our new result. And then from there, it's pretty straightforward. Just multiply the scale onto the x and y values of our original vector onto the new vector. Fun fact, we can do the same thing by saying result is equal to original multiplied by the scale value. And that would be the same as doing what I've outlined here. However, this just clearly shows what our scale is doing. Keep in mind that this line of code can only happen in the current game engine as it supports things like vector manipulation, although I may be wrong. Regardless, what we do is we return back our result. And that's basically it for vector scaling. Let's go ahead and do the same thing for vector rotation. First, let's go ahead and create our result variable. Next, we have to convert our degrees into radians, and lucky for us, Godot has a built-in method to do that. It's called degree to radian, and of course, we need to pass in our degree value. Next, we do the same thing for sine. In this case, the Godot game engine also provides sine, or a method called sine. We pass in the radian to get our sine value. And Godot game engine also provides the same thing for cosine. From there, we do the vector rotation theorem. And that looks to be in order, original x multiplied by cosine minus y sine. And for the new rotated y value, that would be original x multiplied by sine plus original y multiplied by cosine. And seems about right. And from there, we can just return our result. However, you have to keep in mind that this is the Godot game engine, and 0 or anything going in the negative direction goes up and the positive direction goes down. And right now, our formula assumes that we are working in the, and in this case, Cartesian graph system. And again, the Cartesian graph system is where positive values go up and negative values go down. And so in this case, Cartesian graph system does not equal the Godot game engine graph system. So keep that in mind when getting back our value for our paddle movement. However, I'm going to return the result as is because, for example, when we call the vector rotation, we already assume that we are dealing in the Cartesian graph system. And so if maybe I need to do calculations in the Cartesian graph system, it's best to use the vector rotation, because vector rotation by default assumes you are working in the Cartesian graph system. And whatever function calls this, if it needs to flip or convert our result into the Godot game engine system, then let the function handle that. So just something to keep in mind. I'm not going to let this function deal with converting from Cartesian graph into Godot game engine. I'm going to let the function that calls vector rotation to apply the changes necessary to make it fit into our Godot game engine. And as a matter of fact, let's go ahead and do that now. So what we can do is actually go into paddle. And from here, what we will be doing is creating a new function. In this case, let's go ahead and call it change ball direction. And what it will take in is a ball class. From there, we don't want it to actually do anything but change direction. And because we are passing in the ball value, first let's make sure that we get our y position of the ball. And so our variable called ball y is our ball's current y position. Next, we do need a magnitude, and we do need a degree. And this is perfect, because which class better to handle management of magnitude and degree than the paddle class? So let's actually go to the top and create those variables. Next, let's go ahead and actually create those variables. So first, let's just create a magnitude, and what we want is just one value, in this case a max magnitude of 3.0, so between 1 and 3. However, during our calculations, we can actually inverse this, 3 and negative 3. And we can do the same thing for rotation. And there we go. Now from here, our magnitude, which is a float, will equal to our math point conversion. And we pass it in all 5 points: our ball position, the position of our paddle, our position of our paddle, and this is important because we need to add onto that the size. And then from there, our max magnitude and our inverse of max magnitude. And that's basically it for our magnitude. We can actually copy and paste this for our degree value as well. And instead of max magnitude, it's going to be max rotation. Okay, now that everything's set up, we do have a problem. And our magnitude can be any value between positive and negative, and we cannot have that. So this is actually an easy fix. All we need to do is make sure that magnitude is absolute. However, there is one problem, in that our magnitude can be anywhere between 1.0 and 0. And so this is a perfect example of using a ternary operator. In this case, absolute magnitude will be absolute magnitude if our absolute magnitude is greater than or equal to 1.0, else we want that to be 1.0. Now from here, let's go ahead and actually change our current game state. So in the game state, let's go ahead and take a quick look at where we would want to place our paddle code in for changing the ball direction and speed. In this case, we want it in our collisions point to rectangle. We have our ball, we have our player paddle. And because player paddle inherits from paddle, we can actually just call player paddle, change ball direction, and pass it in the ball value. And we can do the same thing for AI as well. And that's basically it. However, if we were to run this code, it would not work because our player paddles and our AI paddle aren't doing anything. Let's actually have the ball class handle the changing of our magnitude and rotation. In this case, first what we need to do is actually go to our inverse x speed and actually change that into its inverse. And in this case, what that will be is, so what that is speed on the x will equal negative speed on the x, and that is how we inverse x speed. Same thing was applied or is applied to the y speed, inverse y speed. Speed.y equals negative speed.y, and we will be using this. So this is actually fairly straightforward. What we need to do is create a function to change rotation and speed, and we need another one that changes magnitude. And so in this case, let's go ahead and create a function to change the magnitude first, because that's the easiest. And this is fairly straightforward. We have a new speed, and it will equal the vector scaling of our current speed and whatever that scale value is, which is passed in as an argument in our change magnitude method. Next, let's go ahead and actually create a function to change the rotation and speed, because we not only want to rotate our ball, but we also want to change the direction our ball is in. Now again, the reason we want to change both rotation and speed is because rotating, or the calculations I have in mind for rotation, is to reset our speed to the base speed, and from there, apply the formula. However, our ball could be moving left or right, and so if it's moving right, then the calculation's fine because our ball's going to move right. However, if our ball is moving left and we change the rotation, then what we essentially do is reset the ball to moving right to do our calculation. And then we need to also apply a flip on the x-axis. So that way, instead of moving right, it moves left. And so it's easier if I just show that in code. So in this case, first, let's inverse the x speed. So that way we get a sense of direction. And then from there, we can calculate whether or not we are moving left or right, which is just a float value. And in this case, what we're saying is, after inversing our speed on the x-axis, if we are moving right, then we want 1.0 to be applied to the rotated value, which means we're just going in the positive direction on the x-axis, which means we are moving right. And so if we're moving right, then we don't need to flip it. However, if we are not moving right, which means we're moving left, then we need negative 1.0, because when we multiply this to the newly calculated rotated value on the x-axis, we flip that. And so instead of moving right, we now move left, which is to the negative direction on the x-axis. From there, it's fairly straightforward. We can just start by rotating. And again, what we are doing is we are calculating rotation based on our base speed, followed by the degree. And based on our degree, that is our rotated value, keep in mind that this calculates in Cartesian graph. And so to fix this into our game engine graph, all we have to do is just inverse the y-axis. From there, what we can do is make sure that our x goes in the direction it's supposed to go. So if it's moving left, it needs to move left. And keep in mind that reset speed, again, is positive. And that's over here. You can see that 400 is positive, vector 2, absolute speed. So keep that in mind. Our base speed moves to the right. But if we inverse and have our ball moving to the left, we still need the newly rotated value to move to the left. And to do that, you just need to find the rotate.x value and multiply that by our variable left or right. If we were going right, we multiply by 1, which does nothing. And if we're moving left, we multiply by negative 1.0, which flips our rotate.x and has it moving left. Now, from there, what we can do is say that our speed will equal our rotate value. And that's basically it. And maybe this is better represented as direction. So change rotation and direction. What we can do is actually create a function called change speed. And I believe I had that earlier. I'm not sure, but regardless, what we can say is speed is equal to speed. And then from here, we can just apply that in our change rotation and direction. And we can do the same thing for our change magnitude. Regardless, now that we have these functions, we can head back to our paddle class. From there, we can just call the ball classes ball change rotation and direction, pass it in degree. Do the same thing for the change of magnitude, which will be magnitude. From here, we can actually test the game and see if it works, and it should. And it works perfectly. Now, when we hit the edge, we move really high. Oh. And there we go. Nothing's random anymore. In the last episode, it was random. However, in this case, let's see if it changes. No, nothing changes. It's good. If I move slightly, it moves slightly. The problem is the angle is too large. Our max rotation is too large. Let's go ahead and actually change that into 75 or something. And we can just mess around with the max rotation value until we get something we are comfortable with. And I'm going to keep it at 75. Regardless, that's basically it for this episode. I'm going to go ahead and upload everything onto GitHub, so please feel free to download that. Well, that's all I have for you in this episode. Thank you for subscribing and thank you for clicking the like button. Again, don't forget that this episode's coding example will be uploaded to GitHub, so please feel free to download that in the description link down below, and I look forward to seeing you on the next episode. Have an amazing day.